about 30 minutes or 40 minutes. Ну, сам поезд, по-моему, идет минут 40, все, он же быстро какой-то очень.
Ну, смотри, да?
Ну да, да, это, сначала какой-то.
Я живу в Дубне, и это будет 3 часа на поезде.
Ну, главное, что на машине уже не быстрее. То есть, когда-то я доезжал там до дома за час 45, но вот все последние годы меньше 2 ни разу не получалось. Потому что я живу относительно, ну, как бы в этой стране.
Ну хорошо, спасибо за приглашение. Грустно, что Кричевер не с нами. Я его не очень хорошо знал, но он всегда был со мной очень дружелюбным. Извини, что я буду на английском читать лекции, потому что одновременно думать и говорить по-русски мне сложно.
А когда вы говорите по-русски, вы думаете по-английски?
Ну, кажется, да.
Удивление там стандартное начало писем было I have to think, so I have to continue in French.
So I don't even remember what the title of the talk was, but so let me say it like this. So from I think it should be necklace Lie bracket. So I'm going to remind you what this is, and if you get nothing else from the talk besides remembering what this is, I hope it's useful. It's a very nice thing. So the necklace Lie bracket, let's say in non-commutative geometry, so our original motivation for studying this was not the necklace Lie bracket, but something called the string Lie bracket in string topology, and how in higher dimensions this should be related to shifted symplectic geometry. And when I began looking around the literature as to what was already known, we realized that the thing we have is a kind of version of the necklace Lie bracket in higher dimensions, and already the usual necklace Lie bracket is very interesting, and we recovered in some way, and maybe get some refinements of it and have more general situations in which we can make sense of it. And so I thought that motivating it in terms of this is something closer to mathematical physics and integrable systems. So let me start with that as motivation. So I'll do the simplest interesting example. I think this was the original example of the necklace Lie bracket. So I want to consider, I'm going to say work over the complex numbers. Any kind of field of characteristic 0 would be fine, but let's be concrete. And then I want to look at the total space of the cotangent bundle of the Lie algebra GLM. So here I'm not using the Lie algebra structure so much, just n by n matrices. And as an affine space, well, as cotangent bundle to an affine space, I can write this as GLN cross GLN dual, and then using the trace pairing, I can rewrite this as GLN cross GLN. And so a point in here I'll think of as just a pair of n by n matrices. And with respect to this identification, you can check the standard symplectic form on the cotangent bundle. Looks like the following. Well, it should be exact. It should be the differential of the Liouville 1 form. So it will be d of trace of y times dx, where d of a matrix means entry-wise. And so this will be trace of dy dx. So this is the setting in which, let's see if I can think. constant.
When you say standard, you include some natural group actions, or what is encoded in the standard?
Well, first it means the usual simplex form on the cotangent level as d of the Liouville 1 form. So this is the fiber direction. So this is kind of, p times dq. I'll write p's and q's in a minute. And the other thing is that indeed it is invariant for the GLN group action here by change of basis. So I forget the other author, but there's Poisson, Kajdan, and maybe Sternberg, I don't remember. So they studied this space in the setting of their construction of the Calabi-Yau system. So for showing that it is completely integrable. And so I'll explain a little bit of what goes into that and how you might hope to generalize this. So to do that, well, we'll have to give a bunch of Hamiltonians. We'll have to compute their Poisson brackets to see that they commute. And then, well, there won't be enough of them on this space, so we'll have to do some Hamiltonian reduction, which will give the phase space with the Calabi-Yau system. So there's a collection of Hamiltonians. I mean, any function is a Hamiltonian, but there's some very natural invariant ones. Misha, please relate to me if there's an important question.
It's Sternberg.
Sternberg.
Constant Sternberg.
Is it the same, what is called in Russian, actionistic перелом?
I think it's the same as Gulen and Sternberg.
Yeah, but I don't know. What is it?
I thought that they constructed Calogera, rational Calogera, as Hamiltonian reduction from this maybe the same. Okay.
So I'm following notes at Ettinghoff. He has a book about this. I confess to not having looked yet at the original paper.
So these three did it in 1978.
I think approximately the same, but I also haven't seen the original paper.
Okay. So I learned this from a very nice set of notes of Ettinghoff on the Calabi-Yau system, which is kind of all I know about integrable systems. So there's a collection of invariant Hamiltonians, which is for every word, let's say W, is a word in non-commuting variables X and Y. So those are living in some free algebra. I'm going to send it, so let's suppose it looks like X I1, Y J1, X IM, Y JM. I just send that, insert the matrices, X and Y. So generic matrices. And then I take the trace of these generic matrices, and that's a function on this space, invariant under simultaneous conjugation of X and Y. So I'll give a name to this function. I'm going to call this function just f of w. And we'd like to know how to compute Poisson brackets of functions, in particular these functions. So if I'm going to introduce names for coordinates. So let's say that Q ij of the generic matrix X is the ijth entry of that matrix, and Pij is, so these are supposed to be canonical coordinates. This will be Yji. It's Ji instead of Ij because that's what happens under the trace band when you pass from the duals. And so the chunk, so let's see, there are conventions about Poisson brackets. I think I did this correctly so that the Poisson bracket mapping to Hamiltonian vector fields is a Lie algebra homomorphism, not an anti-homomorphism. So this will be the usual thing. And then it's a fun calculation, moving these partial derivatives through the trace and seeing what they do to a generic matrix and how this behaves under multiplication. You'll find, so if U, let's say U is A1 through AK, where those are, this is a word in X's and Y's. Maybe I'll write little a's. And V is BL. So you can check that this will be a sum. Let's see. Don't you want to use I and J? I wanted to use K and L. And I've already used N. So I don't know what to put. It's big N prime. So up to a sign, I think I have this right. And this will be sum over K, AK up to A big N, B1, where AK equals X, BL equals Y. So when you take these partial derivatives, this, because it only picks up x coordinates and no y's, so the all other valuations of these coordinate functions on x or y vanish. I'll kill this term, AK. It will appear as a 1 exactly when there's x, otherwise it will give 0, so there's no contribution. And similarly, when I take partial derivatives with respect to PI, I need to have a y to get something on 0. Then there'll be another term which is reversed coming from this. So it'll be KJ, where AK equals Y, BL equals X. So very similar thing. Trace of is simply to show that it's something very explicit.
So the length of this word W is what? Sum of all INGs, yeah? What is, just to understand your notations, what is the length of your word?
So K and J can
I'm asking not about that.
so K can run from 1 to N.
Yeah, about this W. What is the length of this word?
This N is not the same as that N. I just made up a.
Yeah, but each.
So this one, here, the way I wrote it, this was supposed to be something generic. So for a generic word, maybe there's no X leading, maybe there's a J leading. So maybe this is 0. And maybe this is some power.
Yeah,
so I actually don't know what the
but
length of this one is.
the total length is the sum of all I's and J's, yeah?
That's right. And the total length here is exactly N. So I want these to be, the AIs to be in the set X, Y, and similarly to these. Okay. So from this formula, you can set, so what, KSK they looked at a collection of Hamiltonians of the following form. So HI is trace of YI. And either fairly directly or using this formula, you can see that these commute. So this is for I equals 1 to N. So these commute. But there aren't really that many of them relative to the size of the space. So they're not completely integrable. But they become completely integrable in a certain Hamiltonian reduction. So I want to describe the general process for this, in this setting, for what kinds of reductions we consider and how we think of them, where the moment map comes from, and so on, because that will generalize. And then I'll mention, for a particular specialization, you get the Colosio-Moser system, and you can look at Ettinghoff's lectures for the details. So the way I want to think of this is, so whence the moment map, and I want to think about it in a particular way, in a kind of algebraic way which will generalize. So I'm going to look at the free algebra. That was the source of all of the Hamiltonians that I've been considering, these special Hamiltonians. And inside of it, I want to consider a special element. So I'll think of that as a map from a free algebra 1 generator. So I'll just send T to xy minus yx. If I have many pairs of variables, if I had 2 pairs of variables, I had x1 through xn and y1 through yn, I would take sum of commutators. And I also want to consider specializing T. To some value. And now, if I do that, I can take a pushover quotient, I'll call it T lambda, so this is just going to be the free algebra modulo this relation to the commutators should be lambda. So I'm writing it like this for a reason. In this picture, what I want to do is just look at, say, representations of these algebras on an n-dimensional vector space. So let's consider corresponding spaces of n-dimensional representations. What do they look like? You need another floor for your boards. You should take over the floor above this.
That's the best we were able to get. The efforts of Igor Krichever for about 2 years to order these boards.
And n here coincides with the parameter of
GLA.
Greece.
GLA.
N here coincides with the parameter of G.
Yes, this is n of GLN. M is very promiscuous, but I'm trying to be careful about n.
It's small m, so it's just, as I understand, yeah, that these Hamiltonians, they obviously commute, but it's not enough for complete integrability on the whole space.
That's right, because it's very big, right? It's
Yeah,
n
it's
squared,
n
nonsense.
squared.
N squared plus n squared. So you have to do Hamiltonian reduction to find something completely integrable, but it's a useful construction because in the reduction you kind of see what the flow is very nicely. So in representation spaces, what I'll get here, an n-dimensional representation of this is just a pair of matrices. So that's my initial phase space. Down here, I'll just have a single matrix. I just have T acting. And the map will send my pair of matrices XY to the commutator. There's just restriction of representations. Here, well, everything, these are C vector spaces. So there's no interesting way to get a representation on a graph. There's only one of them of dimension n. And this inclusion is just lambda acting as the identity matrix. And then the fiber over this is going to be representations of dimension n of this algebra GLN. So it's just the representations in which the commutator equals lambda times the identity. And now you can check that this in fact is a moment map for the action of change of basis. So for GLN, invertible matrices actually by change of basis. And then you can try to do reduction with respect to this. So take quotient by GLN in every place. You have to be a little bit careful. Maybe you want some genericity assumption on the representations because, for a non-generic representation, maybe there's a nasty stabilizer, there's some singularities, so possibly imposing genericity or doing some kind of geometric invariant theory.
So the only genericity is that lambda is not 0.
So in this case, so just a second. In this case, I think that's right. So the case of interest for Clojure-Moser is L lambda is plus or minus 1. I forget which one.
Doesn't matter. You're risky.
Yeah. So you can take the quotient.
Excuse me, please. You can leave the blackboard.
Yes. Maybe this is a better one.
Yes, this is an option.
Okay. Let me try it like that.
Maybe more convenient for you.
Yes, yes. So you can take the quotient and for lambda plus or minus 1, you find it's the result, so representations of T1 n modular GLN this is smooth, symplectic, of dimension 2n. And in appropriate coordinates. It gives a kind of partial compactification of the Calabi-Yau system. So the phase space you get out of this is a little bit bigger than Calabi-Yau himself wrote down, but the flow extends nicely. And then these Hamiltonians that we had restrict here and they give a complete integrability.
What do you mean by partial quantification? You mean that collisional particles can coincide?
I actually not sure exactly what happens on the boundary. All I mean is that the usual phase space embeds as a dense open space in there. And then people have studied what happens on the boundary. I'm not actually sure myself. Did somebody know? I think this must be right, because when you do the analysis, what happens is up to changing basis, you can assume generically that x has distinct eigenvalues. And this is where you end up seeing the term in the Calabi-Yau potential that has xi minus xj, the potential involving the positions. But non-generically, the eigenvalues could have multiplicity, and then you won't have that formula on the boundary. So I think when the eigenvalues become with multiplicity, you should think of that as the particles colliding. Okay. So what I want to conclude from this actually is to look at this formula and notice that I can take the trace out of the sum. And then I have an expression that makes sense purely in terms of the free algebra. So, in fact, the bracket makes sense already on the free algebra modulo commutators. So this is has a basis of cyclic words. And the fact that you're getting cyclic words is related to the fact that we're taking traces. So I can cyclically permute these. So you can check that the bracket makes sense, and you can write it suggestively in a kind of typical form. And I have to tell you what this means because now I'm inside some non-commutative algebra. So if I have words U and V, let me write a formula and explain what it actually means. So here,
I think for
are you complaining this doesn't make sense? So it doesn't quite make sense yet, but let me say what this means in the non-commutative case. So in a way that will make this formula make sense. Let me try and then see if you still have the comment. So I'll write this as sum. So if I write the word as a product of variables x and y, then this is unambiguous, there's only one term. So it's 1 if this equals x, and it's 0 otherwise. And then I sum over this kind of expression. So I'll have, so for each I, this will be a sum over I. Okay, and similarly for die by die y.
Where use in the right hand side are W's, yeah?
There should have been w's instead of u's. Thank you. So if you interpret die by dx in this sense, as well as die by die y in a similar sense, then this gives a formula here, which matches this formula, and you can check it's actually a Lie bracket here. This is what people call the necklace Lie bracket. And it can be extended. Universal?
This is the same for this. But
So Ramesh says that if you replace this trace by universal trace, projection to model accommodators, then we can.
Yeah, I mean, you could let n go to infinity, for example. So I want.
What is universal trace?
Just the projection from algebra to exposed model accommodators.
not commutator strings, I think. Let's say permutations of letters.
Oh,
Model commutators, it would be commutative algebra, right?
No,
It's not an algebra because commutators don't form an ideal.
It's just about notation. When I see
I just mean it as a
commutator-
sub. It just means it's a subspace. It's not actually an ideal, so the quotient's not an algebra.
Yeah.
Okay, so I can think of the free algebra as the path algebra of a double quiver. So I start with, it's a very simple kind of quiver, so you don't even notice it's a quiver. I have one vertex, one loop, and my other loop, y, I think of as dual to x. So I can do this kind of construction for any quiver. I can double it, where for all edges in Q, I add a dual edge. Here. So the picture looks like this. So going the opposite direction. And this is useful because if I look at, say, representations, so let's say framed representations, not up to change of base, it's just literally representations. Then I could take, that's some affine space. I just have to give you, for each vertex, some vector space. It's its own dimension. For each arrow, I have to get an operator between the corresponding spaces, and so on. And so the cotangent space can be identified with framed representations of the dual quiver, in the same way we identified T star of GLN with GLN cross GLN dual. And then you could play the same game in this situation. So the whole story generalizes. Well, the formal part of the story generalizes. So you can, there's a theorem of, let's see, is it maybe Ginsburg? Maybe the idea was originally due to Kontsevich, at least in this example, of the free algebra, and Volkovan. Lebrun. So you can look at Q, the quiver. I look at its path algebra of the double quiver modulo commutators. So this is what I'm going to call NQ. This has a basis of cyclic words, cyclic paths in the quiver. So this has a necklace Lie bracket given by kind of the same form where I replace X and Y with A and A dual for every edge. And the kind of trace of action map which goes from these cyclic words to functions on these framed representations of the double quiver. This lands in some invariant function, so I can change basis at each vertex. And this intertwines brackets. So on the left-hand side, I have this necklace Lie bracket. On the right-hand side, I have the Poisson bracket for the standard symplectic form on a cotangent space. And now, so this is some very general construction. There are a lot of moving parts for the quiver. You can also choose, write down the moment map in a similar way in terms of some sum of commutators. It's called the pre-projective element. So this is also the setting of Nakajima quiver varieties. They admit a description in terms of Hamiltonian reduction of this sort. And so in each of those cases, you can try to engineer your quiver and engineer Hamiltonians to construct some integrable system you might care about. So this construction has been used, the first example was Kolozhiro-Moser. You can also do trigonometric Kolozhiro-Moser. You can also do, I don't know how to pronounce it, another Dutch name, Roysenaars.
It's impossible to pronounce. So.
Yes.
But what kind of quiver corresponds to trigonometric algebra?
So Ettingolf says, the way he says it, but he doesn't give many details, is that you just change the Hamiltonian and restrict to some open subset of the same thing. It's the same quiver. There's another way to say it, which is to do a kind of multiplicative version of this instead of an additive version, where I put in here T and T inverse, and then I have to introduce some new elements in here so that I can make sense of where T inverse goes to. So instead of a sum of commutators, you have a product. You have a kind of multiplicative version of commutators. So it looks more like relations in a group algebra. So there are different ways to do it.
When you say about this unpronounceable Roysenaars,
Yes.
you also mean trigonometric Roysenaars.
I think both, yes. And so these are cyclic quivers, and this was studied by Charlich.
And spin color, yes? We can get the same.
Sorry?
Spin color.
Yes. So Charlich and a student, Maxime Ferron, have studied this. So there are various examples of this. So this is all kind of motivation. but I hope it's sufficiently interesting that if you don't like what comes next, you can still see that this is some kind of interesting setting in which to do Hamiltonian
What
mechanics.
is important for you is that you have for each quiver some variables defined on the edges of the quiver, yeah? So you have vector spaces on the vertices and these your variables on the edge, and you write down some bracket on these variables,
Yes.
which
is
you defined it, of course. yeah.
already exists at the level of the words in the quiver before you even pass to the moduli space of representations.
These exist for any
Quiver?
also.
Yeah, it works for any quiver. There are no restrictions. Okay, so my goal is the following. So there's also a multiplicative version. So here's a motivating question. This won't be my theorem, but it's a motivating question from the point of view of Hamiltonian mechanics. What would be an elliptic version? And so I'll describe some kind of more general setting into which this fits, and in which I can put as examples elliptic curves appearing in moduli spaces associated to some algebraic data involving elliptic curves. There will be a symplectic form, there will be Hamiltonians, there'll be some kind of formula for the bracket. But then it remains a question as to how you engineer the choice of data to get some elliptic integrable system you care about. And that I don't know the answer to. So I'm going to give you some phase spaces, a very general procedure for producing phase spaces, Hamiltonians, and computing brackets on them, including elliptic cases. So to do this, I'm going to drop quivers, but I'm going to keep this kind of diagram, more generally. So I need to figure out what is it about this diagram which gave me a symplectic form on a moduli space of representations and gave me a formula for computing Poisson brackets. So for this, so the idea is to think of how long did we go? Is it an hour and...
Well, usually we have an hour and a half.
Okay, very good. Okay, so the idea is to think of this diagram. Maybe I should give it a name. As a non-commutative analog of the following topological picture. So I'll just give one example. It could be any oriented surface with boundary. So consider some oriented surface with a boundary component included. And at the level of algebras, I would have the group algebra, just the fundamental group, like this, and then I could pass to group algebras. So this would be around polynomials. This is just the integers. This is the power of t gives you how many times you've gone around the loop. And well, this is whatever it is. I guess it's part of the free group. This is some algebra. In this case, happens to be free. And then, if I'm looking at representations of this, I'm looking at the moduli space of local systems on this surface. And then I could restrict those to the boundary and see what the monodromy is around the boundary component. Then I might like to fix it. So maybe I want to trivialize it so that I can cap this off, or maybe I want it to be given by some particular Jordan normal form, and so on. So I could put a boundary condition. So this might be given by some homomorphism by specializing t to some lambda. Okay? And then if I push on, I'll get some algebra where I have some extra relations in this group algebra where I force the monodromy around the boundary to have some particular, to be central and have some particular value. So in order to formalize this,
don't understand why you.
what's that?
Why, I don't understand why you call the non-commutative.
Well, so this is at least topological. I mean, the algebras, of course, are non-commutative, but I think of, if I'm studying local system, what am I parameterizing when I parameterize representations? I'm parameterizing local systems, which are kind of commutative objects. There's a tensor product of them, where that's related to the fact this is a Hopf algebra. Here, there's just, well, the fact that this is maybe a Hopf algebra is not relevant. Okay. So I'm going to consider very general. So I need to give a definition. So the important thing here is the following. This is oriented, but with boundary. So it doesn't quite have Poincare duality. It has Lefschetz duality. That's the version of Poincare duality relative to a boundary component. However, the boundary itself is closed and oriented. So I first need to tell you what's the non-commutative analog of an oriented space. And this is the notion of Calabi-Yau algebra. So this is Calabi-Yau algebra, or non-commutative oriented space. If I think of an algebra as kind of such that modules over it are some kind of sheaves on my non-commutative space, then this will make sense more of it. So the definition is the following. So given algebra S such that there's a condition. It's a kind of smoothness condition, or a finiteness condition, if you like, such that the diagonal bimodule S, so S acting on itself from the left and right, has a finite projective resolution. So that's a homological finiteness condition. And this is for a commutative algebra that would be saying it's a regular algebra by Serre's criterion for regularity. Okay, then a non-commutative orientation. So people sometimes call it a Calabi-Yau structure. So from that point of view, it's like a non-commutative volume form. Or non-commutative orientation, if you're thinking more topologically, of dimension. So every oriented manifold has a dimension. What is it? Okay, so it's a Hochschild homology class. I'll go back and say exactly what this is. I'm going to call it theta of degree d for my algebra, such that so there's going to be a kind of Poincare duality in a non-commutative sense. So the Hochschild cohomology will play the role of cohomology. The Hochschild homology will play the role of homology. There'll be some shift of degrees. This one is an algebra, this one is a module over this algebra. So I can act with any element on here and get some element there. That's what's responsible for the shift. And the condition is that this is an isomorphism. So I'll give an example. So this is non-commutative Poincare-Duval. So you think of theta as orientation or the non-commutative volume form, and then this is the non-degeneracy condition making it vanish nowhere. So let me give an example, and then if you'd like, I can also give formal definitions of what these things are. Cyclic homology? Yeah, so Roma, I think, is pointing out that what I defined is not quite enough to do everything you want to do. So this, what I've written here is what Ginsburg called the Calabi-Yau algebra. If your algebra S is just a usual algebra, not a differential graded algebra in some non-trivial way, then this turns out to be equivalent to a finer condition. And this finer condition in the DG setting is really necessary to do all the constructions you want. So for people who know what this means, Hochschild homology is what gets associated to some topological field theory associated to this algebra. It gets associated to the circle. So it has some circle action on it. And you require the data of making this class theta homotopy circle fixed. And in cyclic language, this means you have to lift it to a negative cyclic homology class. So I would like to sweep this under the rug, but Roma won't let me.
Give us some example. Yeah?
I will give an example right now. So I'll give the kind of most elementary algebraic example. It also, if you apply it to group algebras, you kind of rediscover the notion of orientation from Poincare duality. This is a little harder to explain. So let me just give a purely algebraic example. So what's the simplest Calabi-Yau variety? The stupidest Calabi-Yau variety, besides a point, is the affine line. And then Hochschild homology, this is kind of a general feature for smooth varieties. You can write Hochschild homology in terms of differential forms. So there's 2 degrees. There's HH0 and HH1. These are homological degrees. It's non-zero in 2 degrees. This turns out to be, so in general, it will be the algebra modulo of the commutators. But in this case, the algebra is commutative, so this is just the functions. And this one turns out to be the one forms. So this is how it works out. The fact that in the commutative case you can write Hochschild homology in terms of differential forms is called the Hochschild-Costant-Rosenberg theorem. So costant appears for 2 independent reasons in this talk. I think it's an S. I don't know which Rosenberg this is. And Hochschild cohomology in the commutative case also emits a kind of geometric description. In terms of Pauli vector fields. So now it lives again in 2 degrees, but in 2 cohomological degrees. So this again will just be functions. In general, it will be the center of the algebra. But in the commutative case, it's just the algebra itself. And this will be the vector fields. In the general smooth commutative algebra, there'll be higher terms involving polyvector fields. And then the action is kind of the obvious one. I can multiply on these, and I can take derivatives here. And I get that, let's see, HH0 plus HH1, if I act on this volume form, this algebraic volume form, is nowhere vanishing on the affine line. Let's see, this will be HH1 mapping to HH0. Okay, so a function here will go to the function times this de Rham differential, so to be an isomorphism in this degree. And here I'll take the pairing of di by dt with dt, and I'll get 1 inside of HH0, and so this will be an isomorphism. And this is reflecting the fact that I have a top degree differential form which is nowhere vanishing. So this is the...
This is theta.
Yes, so theta here is d de Rham t.
And who is D? 0 over D is 1. 1.
Ah, d is 1. Thank you. D is 1. So in general, if I have a Calabi-Yau variety with nowhere vanishing top form, that top form I can take it to be theta, and I take d to be the dimension of the variety. And you can check that this action from Hochschild cohomology on the top form to Hochschild homology will be an isomorphism. You can also check, but this is a little deeper, that if I had a closed oriented manifold, and I looked at, you need some kind of derived version of the group algebra, and then you can check that the orientation in the usual sense also can be used to produce this data. So this is what's happening on the boundary of this picture. I also need a relative version of this, because what I'm really interested in is maybe these oriented manifolds with boundary. So this is an example. Does anyone want a general definition of Hochschild homology and cohomology, or can we just fake it?
If you don't need it.
Yeah, I don't think, if you're willing to believe that there is such a thing. You know, one thing acts on the other, and then the definition makes sense, and that in commutative cases, it's about the action of polyvector fields on differential forms. I think that's enough. Okay. So we also need a relative version. So definition. So given two smooth algebras, it'd be definition construction. In order to make sense of the definition, I have to give some constructions. So given two smooth algebras, say S and T, and a map between them, so you should think of this, in this example, as just a map on group algebras. We have, more or less by definition, so Hochschild homology is natural in maps of algebras. So take Hochschild homology of S. This will map to Hochschild homology of T. And then, by definition, I take kind of the co-fiber of a cone, just like you would in usual topological homology. We would call that relative homology. So by definition, the relative Hochschild homology is what you get over here. And the reason I need this is that the usual duality theory for manifolds with boundary involves the relative homology. It's called Lefschetz duality. So Lefschetz duality is about having some relative homology class which induces an orientation on the boundary, which gives you a duality between relative cohomology and homology. So this is a definition, and then we also have relative Hochschild cohomology. This is a little bit more mysterious. But I can tell you what it is as an algebra. So the reason it's more mysterious is that Hochschild cohomology, like polyvector fields, there was this Chern is supposed to have said that a vector field is like a man and a differential form is like a woman. I'm not sure exactly what it meant. You can try to imagine what he meant. But part of, I think, what he meant is that you can't push forward differential, you can't push forward vector fields. And the way you,
Who was it?
Chern. So Hochschild cohomology doesn't have nice functoriality with respect to maps. But nonetheless, there's a relative version of it. So it's a kind of fiber product. So it turns out both of them map to a common thing, which is kind of endomorphisms of the map between them, thought of as a bimodule. So here, F from S to T gives a bimodule. For instance, well, it's just T. There's T as a bimodule. So T acts on one side of itself and S acts on the other via F. So you can make sense of this fiber product, and then this will act on this sequence. So this will be the relative thing. And you should think of this as like relative cohomology. So then, this acts on every term of this sequence. It acts on here via the projection to Hochschild cohomology of S. It acts on here with respect to Hochschild cohomology of T. And the fact that I took the fiber product makes it so that this map is a map of modules, therefore it acts on the cokernel. So this acts on the sequence. Now I can give it a definition. By the way, for those who have studied Koncevich's approach to deformation quantization, a very important part of that is formality, and also Tamarkin's approach to that is formality of Hochschild cohomology as a Gerstenhaber algebra. So this is formulated in terms of something called the Deligne conjecture, which says that Factual cohomology is acted on by the little disk operand, where I put little disks inside of a bigger disk. And you can prove the Deligne conjecture for this relative factual cohomology. The proof is kind of interesting, and this will be on the archive in a paper with Nick Rosenblum very soon. So the main theorem I want to get today will probably be a few more weeks before it's on the archive, but this kind of input will be available very soon. So you can take a look if you're interested in those kind of formality and Deligne conjecture questions.
Why do you call it conjecture?
What's that?
Why do you call it conjecture?
Well, I mean, why is the Deligne conjecture called a conjecture? I don't know. What will the Riemann hypothesis be called when it becomes a theorem? I'm not sure.
Until it is proved.
Until it is proved. Yeah, I don't know. It's the usage. Who is this? I recognize the voice.
Barannikov.
Huh? Barannikov. Okay, so definition. So given this map of smooth algebras, so you should think like something like free algebras, maybe free algebras with a differential. Of smooth algebras. I want to formulate the notion of relative orientation, and it will be enforcing something like Poincare duality, just for this relative factual homology. So it will look like Lefschetz duality. So a relative Calabi-Yau structure of dimension D, or non-commutative oriented relative orientation. So you should think of this as like a d-dimensional manifold oriented with boundary. Is what? So there's going to be, again, this orientation or volume form. Such that this Lefschetz duality is satisfied. So for the action of relative factual cohomology and relative homology, I should get an isomorphism. Now I can give examples. The simplest example, it's already kind of interesting, and it's related to my favorite diagram, which I've rubbed off. So actually, let me give two examples. I'm going to assert. I mean, there's actually some calculation you have to do that's not entirely easy. So this definition, I wrote a paper with Tobias Dickerhoff, which is kind of the background of what I'm talking about, where we gave this definition. And the paper has theorems that I like, but I mean, somehow the definition is what turned out to be important. So examples. So let me draw this diagram again. Actually, So you could do the double quiver version, but let me just do this very simple version. So notice we already explained why this is one-dimensional Calabi-Yau. There's the volume form on the line. This is one Calabi-Yau. It turns out that this has an essentially unique relative orientation. In this simple example, you could compute this by brute force. You have to compute these groups, see what lives there, see what the action is, but there's a smarter way to do it. So this is essentially unique relative orientation of dimension 2. So you really should think of this as like a non-commutative surface with a boundary component. Also, this also. So this is also has a relative orientation of dimension 2. That's a little more surprising. This looks like it's 0 dimensional.
If we start with actual manifold with boundaries, for instance, example of this like that.
So I didn't quite understand. Did you catch it, Misha?
Was there an exponential variety of the boundary?
Maybe I should add a condition. I don't know if this is at all what Ron was asking, but the analogy should be clear. So there's this condition, and I want the boundary to be oriented as well, typically. I mean, the definition makes sense, as I said, but for the applications, and also in the usual duality theory for manifolds with boundary, I look at, under the connecting map, I look at the image and I require this to be an orientation of the boundary. So, and I require that theta bar is a d minus 1 dimensional orientation on the boundary.
Now, I want to have a direct relation to the manifold with
You want to understand the example of a manifold?
yeah.
So I'd be happy to describe that afterwards. So there's a very nice construction, but it uses the theory of Goodwillie-Jones on computing Hochschild homology or of a category of local systems. And you have to introduce some kind of derived group algebra, the fundamental group. So it can be done nicely, but it will be a kind of digression right now. So let's talk about it afterwards.
So, Chris, so you say that there exists unique relative orientation of dimension 2 where on this?
On this, so the relative orientation is for a map of algebras.
For a map.
Okay? So it's some class in the relative functional homology, and I'm going to require this. So in this case, it's essentially unique such that on the boundary, which is this, I get the thing I wanted on the boundary.
Mm-hmm. And what is theta?
You have to compute. So there are two ways to do it. In this simple example, you can just explicitly compute what the map is in Hochschild homology. This can be done, but it's a little tedious. A better way to do it is to realize that this arrow comes by a kind of general construction, which is called kind of relative Calabi-Yau completion. So associated to any map of algebras, for any algebra, you can form what's called as Calabi-Yau completion. For a variety, what this would mean is I pass from the variety, which doesn't have to have a Wilhelm form, to the total space of its canonical bundle. And that always has a Wilhelm form. So there's a non-commutative version of that. And then for a map of algebras, there's also a kind of non-commutative version of taking a conormal bundle, it turns out. So this map actually arises from some universal construction such that it has to have this structure. This is kind of the smart way to do it. And also the double quiver examples with this pre-projective element also arise by this universal construction. Okay, so I assert that it exists here. After the talk, if someone patiently wants to see the calculation, we can do it.
I just didn't ask about calculation, but about the result of calculation, if it can be written.
It can be written. Yeah. It can be written, and it can be done in some smart way or just with your bare hands. Originally, I realized this with my bare hands, and then found a smarter way to do it. Okay, so what do we get? What is this good for? So what? So there are two theorems that make this observation useful. Maybe I should give another example or two. So I promised elliptic curves. Now I'm going to change notation a bit. Well, I already used S for an algebra. So let me call X. This is a variety, a smooth variety. Of dimension D. For instance, D equals 2. And I'm going to look at a subvariety of it. I require it to be an anticanonical divisor. So this should be zeros of some section of the anticanonical bundle, so top power of the tangent bundle. So for example, I could look at P2. So P2, then the canonical bundle, the anticanonical bundle has degree 3. And so sigma is a cubic. And then the zeros are a cubic curve. Possibly singular, it doesn't matter. So this is a cubic curve. If it's smooth, and you choose a point, it's an elliptic curve. Otherwise, it could be something smooth, but it's also interesting to consider degenerate cases. And then in this situation, we call this I. So here, I was instructed to pretend I don't know what a category is. So I've been talking about algebras. But one reason you might want to remember what a category is because you don't want to work just with algebras, you want to work with some kind of varieties, maybe vector bundles and coherent shapes on them. And so this definition that I wrote down, it actually doesn't have anything to do with maps between algebras. It makes sense for functors between nice categories. So you can check in this situation that if I take a bounded complex, say a vector bundles or coherent sheaves, it doesn't matter if there was isomorphism here, I can push them forward from the subvariety into the ambient variety. Hochschild homology makes sense for varieties. This induces a map in Hochschild homology, so same Hochschild homology, so I can make sense of the definition. So this has a natural relative Calabi-Yau structure. Dimension D. So you should think of this as a kind of algebraic or holomorphic analog of the situation where you have an anticanonical divisor of like oriented manifold with oriented boundary. The boundary here is something Calabi-Yau, in this case an elliptic curve, so it has a holomorphic volume form. X itself doesn't have a holomorphic volume form, but it has some meromorphic volume form with poles along the boundary. So this is holomorphic oriented manifold. With boundary. Okay, so this is another important example. And it turns out here, everything is kind of non-commutative, if you think of this as a free algebra, not a commutative algebra. Here, both objects were commutative, but you can end up examples where it's very mixed. So you can sometimes put an elliptic curve on the boundary of something very non-commutative. So those examples are a bit harder to explain. Maybe I'll save them for discussion after the seminar. Okay. So are there any questions about the kind of logic of the examples? I have about 10 minutes, yeah? So let me state a theorem.
Excuse me. Do you consider this Z as an effective simple divisor or any?
You mean, do I require...
Just set of points or
as a subscheme?
Multiplicities?
I can allow multiplicities. I mean,
But-
for simplicity, take it to be smooth, but it doesn't matter. So I can just consider...
But in the case of, say,
It can be...
some curve and points on the curve.
It can be very non-reduced. It could be a triple line.
Okay.
So any scheme which is the zeros of a cubic.
Like in Donaldson construction. You know this?
No?
Okay, I'll tell you later.
Okay. So, but it doesn't matter. It can be really the vanishing of any cubic considered as a scheme. Okay, so let me state, I have to state kind of two theorems. So one of them is kind of where do I get these moduli spaces from, and what structures do they have? So this is with, could be deeper hole. So those papers are on the archive. There are two of them about relative Calabi-Yau structures. So I'll state special cases in terms of algebras, because that's more concrete, but it works for categories and functors. And I'll specialize to d equals 2, because it works for all dimensions, but it's harder to describe what it means. It uses shifted symplectic geometry. So special case. So it says that, suppose I have a diagram like this, a map of algebras, S to T, maybe another map. This might be the complex numbers, it might be something else. So both of these are relative Calabi-Yau of dimension 2. And there's a little bit of a compatibility between them. They're kind of compatible on the boundaries. So I could restrict the form here and there, and I have to identify them on the boundary. So compatible on the boundary. And here, this is the push-off. It's kind of the algebra I get by amalgamating these two along S. So this is part A. So then, this amalgamation, I'm calling it amalgamation because if these were group algebras, that's really what it would be. Then this is Calabi-Yau of dimension 2 without boundary. So in the topological case, what we've done is we had two surfaces with a common boundary component, we glue them together along that common boundary component and closed off the surface. Okay, so this is kind of non-commutative cowords oriented. This also is related to what people call fusion for multiplicative quiver varieties. This is another story. So that's part B, and then that's part A. And part B is what happens when you pass to, say, moduli spaces of representations. Part B says passing to moduli spaces of representations. We got a pullback. So that's just because we have a push out there. So let me write it like this. This is, I'm going to write MT for moduli space of representations. I don't care what the dimension is. I don't even care they can be complexes of representations. So what's important, so this is a pullback, that's formal. What's interesting is what does the relative Calabi-Yau structure do for you? So this becomes Poisson. This becomes Poisson. And this becomes symplectic. So what you have to do to prove a theorem like this is you have to see how this Hochschild type data. I said that in the commutative case, Hochschild homology corresponded to differential forms. It's also true that if you start with something totally non-commutative, but then you pass to its moduli space of representations, you can turn a Hochschild homology class into differential forms on the moduli space. So that's the idea of what you have to do to prove this. So that's one thing. So that produces something like this setting of Hamiltonian reduction that I introduced in the beginning. So you should think this was T star GLN, this was GLN, this is like a moment map. This is imposing some relations for the reduction, some conditions in the reduction, and then in the reduction I get something symplectic. So if you apply it to this example, this is what you get. In particular, this algebra is 2 Calabi-Yau. And the moduli space of its representations is symplectic. So that's one theorem.
Please, excuse me, may I interrupt you? Я надеюсь, все узнали то, что мы разбирали сегодня на первом семинаре. Нет? Это прямо.
Какой первый семинар? Есть еще семинар?
Нет,
We had a student seminar earlier today, and we considered flat connections on a two-dimensional surface with boundary for soft structures, symplectic ellipses.
Yeah. So it does. These things can be those things can be described in these terms. So finally, I have 0 minutes. So that theorem is somehow about how to construct phase spaces and Hamiltonian reduction. The other theorem is about how to construct Hamiltonians and compute their brackets. So given S to T, with relative Calabi-Yau structure at dimension 2. There's also a dimension D version. There's a DG Lie algebra. There's a DG Lie algebra structure so the original necklace Lie bracket lived on T-mod commutators. We need some kind of derived version of T-mod commutators. So that derived version is called cyclic homology. And whatever it is, in degree 0, is T-mod commutators. There's kind of derived functors of this. So there's some natural DG Lie algebra structure on this, which in this standard case gives the usual Lie bracket, but it's a chain level construction. In the topological case, it gives the Chas-Sullivan string bracket. And a trace of action Lie algebra map. So this goes from cyclic homology of T to, so this moduli space here will be Poisson. So we'll have a Poisson structure on the functions. That can be done at the chain level. So in this Poisson moduli space, the derived global functions has a Poisson bracket. And this is a DG Lie algebra map. So every cyclic class gives kind of Hamiltonians here. And you can also show that it behaves well in this kind of reduction setting. So I could also study this just for symplectus things. That's a special case of Poisson. There would be some other Lie algebra acting there. And this one would map to that one and act on the reduction. So this is, the moral of this is, in the usual necklace Lie bracket setting, the kind of input data is very algebraic and rational, or at most kind of multiplicative. So on the boundary, I have something which is polynomial algebra, maybe Laurent series algebra, Laurent polynomial algebra. Here, I can construct more general symplectic moduli spaces by some kind of reduction involving something elliptic living on the boundary. We have some examples, but I don't yet know how to engineer those examples to produce kind of well-known, interesting elliptic integrable systems. So that's a project for the future.
So no elliptic algebra model.
I don't know yet. So part of it is that I open a paper on elliptic Calogier-Moser and I don't understand it yet. So I mean that's what it really comes out. I need to just sit down for some time and understand what's going on, and then see how to engineer it in generalizations in this setting.
Thank you.